Okay, welcome back everyone. In this next video, we're going to continue discussing the concept of capacitance. And in this part, we're going to be looking at what capacitors actually do in circuits and how they combine. So in real integrated circuits, in many electronics applications, you're going to want to have a variety of capacitors, and then later on we'll learn about resistors and inductors. And it's going to be important to understand what happens to these things when we combine them in circuits. So first, let's just think about what this circuit is going to look like. We're going to have a capacitor at the top, which is represented by those parallel plates, and at the bottom we have a voltage. So the way that we think about this is that we have positive charge on one side and negative charge on the other. Another way that you sometimes see a capacitor is like this. Okay, so if you have capacitors in series, what do they do? Well, so let's say we have three capacitors, C1, C2, and C3. So now imagine that capacitor C1 has positive charge sitting here. Well, what's going to happen over here? It's going to become negative. And think about what's going to happen because that's negative. Those negatives are probably going to come from this side, which becomes positive, leaving behind more negative. And then this will become positive, leaving behind more negatives. It's probably better to say that the positives are left behind when the negatives move. And in this case, the flow of all the negatives is going to be this way. But for reasons that we'll talk about later, we usually talk about the flow of positive charge, which would be this way. But more on that later. So in a series circuit like this, basically we have the equation that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So the question is, where does this come from? Well, first of all, capacitors in series all have the same charge. And why is that? Well, we talked about this on the previous slide, but if I have plus and minus, and then plus and minus, and I have Q, then this will also be Q. So really what we're talking about is charging by induction and also conduction. So if the combination has a charge of Q, then each capacitor in the series also has a charge of Q. So this occurs because the capacitors must get their charge from adjacent capacitors. So the charge just moves from one to the other, giving each capacitor the same charge. The voltage difference, therefore, is going to vary inversely with the capacitance of each one, according to delta V equals Q over C. And remember where that comes from is a definition of capacitance as charge over voltage. So that turns into this. Finally, we can go through our discussion here that they have the same charge, but the electric potential is divided up amongst them. In other words, if you think about electric fields, there's one field, there's another field, and there's another field. So as charge moves across these three electric fields, it's going to experience three voltage differences, V1, V2, and V3. And the sum of those will be the total voltage, V total. Now we'll be talking more about this when we discuss circuits, and we'll use the analogy that V1, V2, and V3 are kind of like mini waterfalls or steps that the electrons are moving down. But for now, we'll just leave it at this, and we'll recognize that V is equal to Q over C. So we replace this in our expression up here to obtain Q total over C total equals Q1 over C1 plus Q2 over C2 plus Q3 over C3. Therefore, the equivalent capacitance can be calculated, knowing that Q total is the same as Q1, which is the same as Q2, which is the same as Q3 for reasons that we just discussed. So these all cancel out, and you simply get 1 over the total capacitance is the sum of 1 over the individual capacitances. Now keep this equation in mind, because when we do resistors, it'll be exactly the opposite. That resistors in series will add up and so on. But keep this in mind. Well, what happens if we have capacitors in parallel? Meaning that we have more than one path. So now we have C1, C2, and C3 that all have different paths that the charge can move through. In this parallel circuit, we're going to claim that each of these capacitances will simply add up to give us our equivalent. So where does this come from? Well, first of all, capacitors in parallel all have the same potential difference across their plates, meaning that if I go back to this picture, if I go back to this picture and you think about this as a charge going through this circuit, well, it has three choices. It can come up through this first one, go through the second, go through the third. And in each case, it's going to experience an electric field, and the voltage difference across that electric field will be the same as that provided by the battery. So then we can say that if the combination of capacitors has charge Q, then all of them add up to equal Q. Okay, so in other words, Q1 for C1 plus Q2 for C2 plus Q3 for C3 will equal Q total. Another way to think about this is that you have different compartments that the charge can sit in, as opposed to when it was series, it was basically parts of the same compartment. And we can also say that the larger the capacitance, the larger the fraction of the total charge, because remember that delta V is constant. So how does that work? Well, we claim that the voltage is the same. So that means that Vt is equal to V1, which is equal to V2, which is equal to V3. Now, if we accept that, the total charge is going to be Q1 plus Q2 plus Q3, and we also know that Q is equal to CV. We take that and plug that into here, and we get CTVT is C1V1 plus C2V2 plus C3V3, and the V's will cancel, giving us the equation that the total capacitance in parallel is the sum of the individual capacitances. So let's see an example of this. Let's find out the equivalent capacitance of this configuration. So when we do these circuit problems, one thing that's useful is to draw another picture that is simplified from the previous picture. And you can just do one step at a time. And then as you go, keep making more simple pictures. Now this one we only have to do in 2 steps. This isn't going to be too bad. And the first step is to realize that we have 2 examples or 2 branches of capacitors in parallel. So we can rewrite this as the top one left alone, and the middle branch is actually 2 parallel capacitors that get turned into 1. But the question is, how much capacitance is that? And then the bottom branch has 3 equal capacitances that are again combined into 1. Okay? And how much is that? Well, let's start with that. We know that in parallel, we must take the reciprocal of the sum of the reciprocals. So 1 over C total for this combination is 1 over C plus 1 over C, which is 2 over C. And that just means that C total for that particular path will be C over 2. So that means that for this middle branch, it's going to turn into C over 2, whatever C is. Whoops. Stylus is not cooperating today. So that's C over 2. Likewise, for this chunk here, we're going to have 1 over C total is 1 over C plus 1 over C plus 1 over C, which means that C total for that particular one will be C over 3. So this bottom branch will be C over 3. And now the last step is to take this picture and to turn it into a circuit that just has one capacitor, and that will be C equivalent. So in the first step, we've combined the middle branch into one capacitor and the bottom branch into one capacitor, and now we're going to be combining the three branches together. And remember that when capacitors are in parallel, we simply add them. So C total for parallel is going to be C plus C over 2 plus C over 3. Common denominator is 6. Whoops. So that's 6C over 6, 3C over 6, and 2C over 6, which gives us a total of 11/6 C. So whatever the capacitance C is of an individual, the equivalent capacitance of the configuration is going to be 11/6 of that. Okay. Now, the next example is going to be a little bit more complicated, and this is point B down here. We want to find the equivalent capacitance between points A and B, and we know that the potential difference between points A and B is 10 volts, and we want to find out how much charge is stored on C3, which is right in the middle here. And we're given numbers for all of these, so we're just going to write these real quick. I'll leave off the micro, but when I do calculations, I'll put it back. Those are 5, this is 2, these are 10, and these are 10. Okay, now the first step is going to be to redraw the circuit a little bit simplified. And to do this, we recognize that this capacitor C1 and this capacitor C2 are in series with each other, and this capacitor C1 and this capacitor C2 are in series with each other, and this C2 and this C2 are in parallel with each other. So let's rewrite the circuit looking like this. Here's point A, and let's just say that now we have 3 branches at the top, and that represents, the first one represents C1 and C2 put together, and then C3 is going to be left unchanged for now, and then we're going to have C1 and C2 again. Then there's a little middle part, and then that capacitor will be C2 and C2 put together in parallel. And then we'll have point B right here. Okay, so you can do multiple steps at once, but you don't have to do all the steps. And we can just recognize, since this C1 and this C2 are in series, to get that capacitance, maybe we could call it C12. So 1 over C12 is 1 over 5 plus 1 over 10. Common denominators, and we recognize that C12 is 10/3. So this guy right here is 10/3, and that's microfarads. I'm not writing units right now. And this guy right here is also 10/3, and this guy in the middle is just simply 2. Likewise, I have C2 and C2 in parallel, and the rule for that is we just add them together to get 20. So what I'm doing is I'm writing new capacitances in blue, but I think that it's probably going to be better if I shift my scheme here. So I'm going to put capacitance in red. So 10/3. This is going to be 10/3. And then this is going to be 10/3. Okay, and then, oh, sorry, automatic pilot. That'll be 20 and that'll be 2. Okay, so that is kind of our intermediate circuit. And then the last step, well, there's 2 kind of last steps. We'll take these that are in parallel with each other, the 10/3, the 2, and the 10/3, and we simply add those up. So it's 20/3 and 6/3. So we have a capacitor here of 26/3, and that's point A. And then we have 20, and that's point B. So that's kind of our next step. And then the last step is to put those 2 together so that we have point A and 1 capacitor and point B. And that's going to be, well, we have to use our rule again, that 1 over 26/3 plus 1 over 20 is 1 over C equivalent. So that gets a little messy, but basically what we have is 3/26 plus 1/20 equals 1 over C equivalent, and the best common denominator I can come up with, just multiplying them together. Maybe you can do better, but this one, for example, is 20, so that's going to be 60 right there, and this will be times 26, so that'll be 26. So that means that C equivalent is going to be 520 over 86, which I have calculated out to be approximately 6.05, and then we finally put a unit, microfarads. Okay, so what I'm going to do now is I'm going to pause and redraw all of these diagrams so that we can see how to work backwards and to calculate the potential difference, to find out the charge that's stored on C3, because we have a little bit of work to do before we can get Q3 that's stored on C3. So let me pause and I'll be back with you in a moment. Okay, so we're back, and what I've done is I've redrawn not all of the steps, but 3 of the steps, and you'll see that we're starting with the most simple version, where this is the equivalent capacitance of the circuit, and then we've split that up into what it was, where we had 26/3 and 20, and then we've split up the 26/3 into 10/3, 2, and 10/3, and we've left the 20 alone. So if we look at our previous slide, then we can see that there's more to do, but we don't have to, because what we're looking for is the charge that's stored on C3. And so that's going to be basically, we're going to be zeroing in on this guy right here. Okay, so all of these numbers in blue are capacitance. And there's actually 3 quantities that we need to know. We need to know capacitance, we need to know charge, and we need to know voltage. And the equation that ties all three together is C is equal to Q over V, or Q equals CV. So we can use either of those. Now, what we're told is that the voltage between A and B is 10 volts. So VAB is equal to 10. So there's 10 volts right here. And so that's V. And so we can automatically calculate charge. I'll do charge in green just to be consistent. So that means that QAB, so the total charge for this equivalent circuit, is going to be C equivalent times V, and that is 60.5 microcoulombs. Okay, now we know that in series, charge is the same. So that means that this capacitor right here has 60.5 microcoulombs for 26/3, And this guy also has 60.5 microcoulombs. So the charge is the same, but the voltage is going to split up. And in order to find the voltage in this next step, we have to apply V is equal to Q over C. So if we do that for this one, we get 60.5 microcoulombs over 26/3 microfarads, which is approximately 6.98 volts, give or take with some rounding. And for this one right here, it'll be the same idea, 60.5 microcoulombs over 20 microfarads, and that's going to be about 3.02-ish volts. Now notice one thing, those add up to give you 10 volts, and that has to be true in series. But also notice that the one that has more capacitance, the one that has more capacitance is actually going to have less voltage because C and V are inversely related. Okay, now the last thing that we do is we make note that when we expand this one further, that the 10/3, the 2, and the other 10/3 are all in parallel, which means that they have the same voltage, 6.98, 6.98, and 6.98. So to answer our question, the voltage on C3 is 6.98 volts, give or take. And then if we wanted to, we could go back and we could determine the various charges, but we don't need to do that right now. So we're going to stop here, and next time we're going to wrap things up by talking about the energy that's stored in a capacitor as well as dielectrics.